In this video, we're going to talk about the distance from a point to a plane. The distance from the point P naught, X naught, Y naught, Z naught to the plane with equation AX plus BY plus CZ plus D equals 0 is given by the formula D equals absolute value of AX naught plus BY naught plus CZ naught plus D all over the square root of A squared plus B squared plus C squared. Now, we have a proof of that formula that we develop in another video. But right now, let's just do a few user-friendly examples. Suppose we want to find the distance from the point -1 to -4 to the plane with the equation 8x minus 4y plus 8z plus 3 equals 0. Well, we know A will be 8, and B will be -4, and C will be 8, and D will be 3. And we know X naught will be -1, and Y naught will be 2, and Z naught will be -4. Using that information, we'll plug the values into the formula. And ultimately, what we'll get is the absolute value of -45 all over the square root of 144, which will be 45 over 12, or simplified, 15 over 4. So the point is 15 over 4 units from the plane. Now suppose we wanted to determine the distance from the point 9, 1, -2 to the plane given by the vector equation shown. Well, for our formula to work, we need the Cartesian equation of the plane. So what we can do is determine the normal of the plane by crossing the two direction vectors. So we're going to determine the vector 1, 2, 4 crossed with 3, -2, -8. And we set up our cross product process. And when we do that, we get the vector -8, 20, -8. So that is the normal vector. We can multiply that through by -1/4 to reduce it to 2, -5, 2, because right now all we're really trying to do is get the equation of the plane. We're then going to, since -2, 1, -4 is a position vector for the plane, that means the point -2, 1, -4 is a point on the plane. So we're going to plug that point into the equation 2x minus 5y plus 2z plus d equals 0. And when we do that, we get ultimately -4 minus 5 minus 8 plus d equals 0. In other words, d equals 17. So now we know that the equation of the plane is 2x minus 5y plus 2z plus 17 equals 0. So A is equal to 2, and B is equal to -5, and C is equal to 2, and D is equal to 17. And X naught is 9, and Y naught is 1, and Z naught is -2. And we plug those values into this formula. And ultimately, we end up with the absolute value of 26 over the square root of 33. And so we get 26 over root 33, and we can rationalize and get 26 root 33 over 33. And so that's the distance from that point to that plane. Now, suppose we want to determine the distance between the two planes shown. Well, we know that the distance is consistent, so we just need to find a point on one of the planes and get the distance from that point to the other plane. So, like it says here, each plane has the normal vector 2, -1, 2, so the planes are parallel. This means they're a constant distance apart, and all we need to do is find a point on one of the planes and determine the distance from that point, it should say, from that point to the other plane. That word right there should be point. Okay, and so we're going to find a point on plane 1 and determine the distance from that point to plane 2. To determine a point x, y, z on plane 1, we'll assign a value to 2 of x, y, and z, and then solve for the other. So we can give any value to any one of those, any two of those that we want. I often like to let x equals 0 and y equals 0, and then just solve for z. So if I let x equals 0 and y equals 0, then what I end up with is 2 times 0 minus 0 plus 2z plus 4 equals 0, which ultimately means that z is equal to -2. What that means is that I've got the point 0, 0, negative 2 on the plane. And all I'm going to do now is I'm going to try and find the distance from the point 0, 0, negative 2 to plane 2. So plane 2 has the equation shown here. And so I've got my value of A, B, C, and D. And I've got my value of x naught, y naught, and z naught. And I plug those into the formula. And when I do all that work, I end up ultimately with the absolute value of 12 over the square root of 9. And the absolute value of 12, of course, is 12, and the square root of 9 is 3. So ultimately I get 12 over 3, which is 4. Now, what if we wanted to determine the shortest distance between the two skew lines shown? There's a couple ways of doing this. Method 1, what we can do is simply make two planes and get the distance between them. We can simply get the plane 0, 2, 4 plus t 1, negative 2, 1 plus s 1, 0, 1. And notice all we did here is we kept line 1 intact, but added the direction vector from the second plane to it. And then our second plane will be where we keep line 2 intact. And then we add the direction vector from the first line to it. And so what we've done is we sort of leave both lines alone, but in each case we steal the other direction vector as well, given a second direction vector. Now if you look here, what we've got are two planes, each of which have the same two direction vectors, so the planes are obviously parallel, but they're likely not coincident. So once we do that, we simply are going to find the cross product of these two direction vectors. And when we do that, we get 2, 2, 2. And obviously, we have the same two direction vectors here as we have here. So getting those two direction vectors, crossing those two direction vectors, we obviously get 2, 2, 2 again. We literally did the same work on the left side and the right side. So what we've got on both the left side and the right side is that the normal of the plane is 2, 2, 2. So since it's a normal and we're trying to get a Cartesian equation, we'll consider it to be 1, 1, 1. And so what we can do then is on the first plane, we see here that we've got a normal vector of 1, 1, 1. So the equation of our plane is x plus y plus z plus d equals 0. We're going to sub in the point 0, 2, 4 and solve for d and get negative 6. So we've got the plane x plus y minus 6 equals 0. Over here, since we were crossing the same two direction vectors, we obviously have the same normal. So the equation of our plane is x plus y plus z plus d equals 0. We can sub in the point negative 2, negative 5, 4. We get d is equal to 3. And so the second plane would have the equation x plus y plus z plus 3 equals 0. And so basically what we've established is that to get the distance between, the shortest distance between the two skew lines would be, the two skew lines shown in the question would be the same as getting the distance between the parallel planes given here. The shortest distance between these two skew lines is the same as the consistent distance between these two planes. That's kind of interesting. And so we just need to find a point on one of the planes. Well, we know 0, 2, 4 is a point on the first plane already. And equivalently, for what it's worth, we know negative 2, negative 5, 4 is on the second plane. So really all we need to do is find out how far is 0, 2, 4, that point, from the plane x plus y plus z plus 3 equals 0. Or equivalently, how far is the point negative 2, negative 5, 4 from the plane x plus y plus z minus 6 equals 0. Either one is sufficient to get the job done. So why don't we just determine the distance from 0, 2, 4 to the second plane. Using the formula, we get, we get ax naught plus by naught plus cz naught plus d equals 0. It just becomes 0 plus 2 plus 4 plus 3 all over the square root of 3 ultimately. So we get 9 over root 3, which is the same as 9 root 3 over 3. And then this 9 and this 3 simplify a bit, and that distance is 3 root 3. So that's one way of doing it. Now, a different way of doing it, which I actually kind of like because this way of doing it is correct. You don't actually have to find the equation of each plane, just find the equation of one of them and get the position vector from the other line and determine the distance from that point to the other plane. Now, back to that same question though, there's another method which I actually like a little bit more. The reason I like this other method just a little bit more is because it lets us find the point on each one of these skew lines which is representing the shortest distance. See, we've got these two skew lines in three-dimensional space, and there's a shortest distance between them. And we just found out a way to do it, but what we never found in our way of doing it is what is the actual point on each one of those lines that is representing that shortest distance. So what we're going to do in the second example is the following. First, we're going to figure out what is the parametric equations of that first line. Well, the parametric equations are x equals t, y equals 2 minus 2t, and z equals 4 plus t. What that means is that every point on that first line has the coordinates t, 2 minus 2t, 4 plus t. And then the second line has the parametric expressions, parametric equations, negative 2 plus s, y equals negative 5, and z equals 4 minus s. And what that means is that every point on the second line will have the coordinates negative 2 plus s, negative 5, and 4 minus s. Okay? So what we have written in the typed language here is that the parametric expressions for line 1 are shown here, and that any random point on line 1, as I stated earlier, will have these coordinates. And then similarly, the parametric equations for line 2 are as I stated earlier, and so any random point Q on line 2 will have these coordinates. Now, a vector between a random point on line 1 and a random point on line 2 would therefore be given by PQ, which would be the parametric expression for x for point Q minus the parametric expression for x for point P, comma, parametric expression for y in point Q minus the parametric expression for y in point P. Parametric expression for y in point Q, parametric expression for z in point Q minus parametric expression for z in point P. When you do a little bit of distributing here, we have to distribute that minus sign, and we have to distribute this minus sign, and obviously that minus sign as well. When you do a little bit of simplifying, you get the vector PQ, which is given by this. The x component of that vector will be negative 2 plus s minus t, the y component will be negative 7 plus 2t, and the z component will be negative s minus t. That's the vector between any random point on line 1 to a random point on line 2. Now, why is that significant? Well, somewhere on line 1 is a unique point P, and somewhere on line 2 is a unique point Q, such that the vector connecting P and Q is perpendicular to both line 1 and to line 2. And since the lines are skewed, there's only one point P on line 1, and there's only one such point Q on line 2. Okay? Now, I'm giving you a drawing here, and you might think, well, those aren't perpendicular lines, but remember, it's an attempt to draw on a two-dimensional surface skew line, so that drawing's not really ideal. Okay? Now, what's happening here is really cool. PQ, the vector here, this PQ vector, is perpendicular to line 1. Here, so this PQ vector is perpendicular to line 1. That means it's perpendicular to the direction vector of line 1. And this PQ vector, the exact same vector, is perpendicular to line 2, meaning it's perpendicular to the direction vector of line 2. So, since PQ is perpendicular to the direction vector of line 1, that means the vector PQ that we solved for earlier, dotted with the direction vector of line 1, will be 0. The direction vector of line 1 is 1, negative 2, 1. So we just multiply 1 times this expression plus negative 2 times this expression plus 1 times this expression, and that'll equal 0. We distribute in that negative 2, and we do a little bit of solving, and we end up with 12 equals 6t. So then we're going to take that same vector PQ, and we're going to dot it with the direction vector for line 2. Well, the direction vector for line 2 is 1, 0, 1. So multiplying 1 by this expression, and then adding 0 times this expression, and then adding negative 1 times this expression, and setting it equal to 0, after simplifying, ultimately means 2s equals 2. So if 12 equals 6t and 2s equals 2, it's pretty easy to solve. T is going to be 2 and s is going to be 1. Now, like it says here, often in a question like that, we get 2 equations and 2 unknowns, and then we need to use elimination or substitution to solve for s and t. This example worked out a bit more smoothly, and we can just solve each one individually. So, like we said, obviously, if 12 equals 6t, t is 2, and if 2s equals 2, s is 1. So plugging t equals 2 into the line that has a parametric, that has t as a parameter, we get that the point P is 2, negative 2, 6. And plugging an s value of 1 into the line with s as a parameter tells us that point Q is negative 1, negative 5, 3. So the vector connecting 2, negative 2, 6 and Q, negative 1, negative 5, 3 is therefore perpendicular to each of the lines. That means the distance between those 2 points is the shortest distance between any 2 points on the line. So now we just need to determine the distance between those 2 points. So we're just going to recall our diagram we had earlier. We've now actually determined the coordinates of those points. And we can say that the PQ is simply equal to negative 3, negative 3, negative 3, because it's the vector PQ is just going to be equal to negative 1 minus 2, which is negative 3, and then negative 5 minus negative 2, which is negative 3, and then 3 minus 6, which is negative 3. So that's the vector from P to Q. We just need to determine the magnitude of that vector. The magnitude of that vector is root 27, which is the same as 3 root 3. And the shortest distance between the two skew lines is 3 root 3 units. Now that is the same answer we got the last time. The last method was a little shorter, but like we say, the advantage of the second method is you actually find the point on each line that gives the shortest distance between the lines.